Hello everybody, we are Team 6 and welcome to our final presentation. For our product, we are doing a desk fan and we're expecting our primary customers to be household and our secondary customers to be office and industrial use. Our quantity is 100,000 units per year in total. For our primary customer, we are looking at households and we want to circulate air, it to be lightweight, portable, and aesthetic, and that quantity is 80,000 units per year. Our secondary customer, we need it to be robust, cost-effective, quiet, and that quantity is 20,000 units per year. Here is an overview of our fast diagram and all the functives we needed. Here is our bottom-up assembly sequence diagram, where you can see we start with base plate, have fan casing, and motor housing as sub-assemblies. Here's our top-down assembly where we start with motor housing and have fan casing and base assembly as sub-assemblies. Our assembly sequence analysis diagram was used to determine that bottom-up assembly is the one that we will continue with for the rest of the presentation. Here you can see our functional component mapping matrix, which describes each functive that each component relates to. This is our bill of materials. As you can see, the total price of our desk fan comes out to $19.68, with a major cost of that being the button assembly. Here's the quad chart, which shows that the button assembly, the rotational lock pin, and the logo all should be considered for elimination. Our functional comparison between our primary and secondary customers is all the same, except for the primary customer is the only one that needs to allow rotation in the desk fan. For our component comparison, the different components between primary and secondary are the button assembly, fan column, base plate, rotational lock pin, and gear assembly. Here's our product family design assembly sequence. The top one is the original and the bottom one is after we delayed differentiation. Here is the CAD of our primary and secondary variants. You can see the differences with the rotational lock pin. We replaced it with a speed dial knob on the secondary variant. With getting rid of the button assembly on the base, we had to change both the base and the column of the second variant as well. Here's the assembly time for our design for manual assembly of our primary variant. You can see it's 141 seconds. Our theoretical minimum number of parts is 5, which gives us a manual assembly efficiency of 17.4%. Using that, we decided that the module part that we would be redesigning is our base. According to our FCMM, that provides support and enhances portability. Our quad chart says keep as is, but we chose it because we can improve the ease of assembly and reduce fasteners. Our platform part is the rear casing, and the FCMM says it prevents injuries. Our quad chart also says keep as is, but we can easily reduce fasteners on that as well. Here's our rear casing manual assembly change. As you can see in the original, we had rotational lock mechanisms that clamped it to the front casing, but it is changed in our redesign part to be snap fits, which you can see here on this slide. Here is the base manual assembly redesign. As you can see, we reduced the amount of fasteners from 4 to 2 and included locating features on it. Here you can see our redesigned DfMA, where we improved by about 2.5 seconds in total. This increased our manual assembly efficiency to 17.7%, which is a small increase. However, the ease of assembly due to reduced fasteners was significantly increased.
Now moving to the design for automated assembly, we took a casing as a platform and 3 parts: logo plate, fastener, and rear fan casing nut for the calculation. This is the manufacturing process of front casing. Rods were welded to the sheet metal plate, which were drawn and finally welded with the outer ring. Here is the assembly cost. Low importance and high cost parts were eliminated, which were logo plate and fasteners, while rear fan casing nut was redesigned. For the redesign, the logo was considered as an individual part, which was to be fastened on the front casing. But now, after the redesign, we have simply replaced it with a single plate on which the logo is to be stickered. The second part was rear fan casing nut, which was designed from the shape on the left to the shape on the right, which is circular, to allow a hand and tool access. Finally, we have reduced the number of parts from 7 to 2, and we have around 80% reduction in the total cost, which is from $6.5 to $1.6.
So here we have a 2D image of our base plate showing our critical dimensions along with our tolerance of 0.2. This is our process selection chart for our base plate with the material of ABS, which eliminates most processes. And then using the rest of the criteria, we were able to determine machining and injection molding, and we ended up selecting injection molding as a process. The process selection chart for our front casing is using low carbon steel, which eliminates most processes. And using the rest of the criteria, we were able to determine sheet metalworking and machining as the two options, and we ended up going with machining.
So after redesigning the base plate for design for manual assembly, we estimated the manufacturing cost for it through analytical method and we got $3.5. After the cost determination, we to check the manufacturability of the base plate, we ran it through the DfM Pro and got 40 high-level recommendations. So we decided to reduce the complexity of the part and redesign the entire base. While redesigning, we made sure that we follow all the recommendations, like making sure that we have uniform wall thickness all over the part, giving drafts to all the vertical faces, and locating features, the holes, and reducing the complexity to use less material. After redesigning the part to a simpler version, we again calculated the manufacturing cost through analytical method and we got $2.6, which was around $0.9 reduction, which was mainly due to the material reduction.
But for the redesign of our front casing, the process used was blanking and bending, and using the analytical method, we were able to come out with a cost of $1.06. Using a quote on hubs for our front plate, we were able to get a price of just over 10 cents. We use a quantity of 100,000 units because it will be used on both of our variants. And then to adjust for the 20% profit in hubs, the updated price would be just over 8 cents. Our design of product service system suggestions are to provide a helpline for customer questions and offer replacement parts available for purchase. This would benefit the customer experience by allowing customers to save money by just allowing the individual parts instead of an entirely new fan, and the helpline would allow customers to troubleshoot any problems that they would run into. The environmental impact of this would be to reduce the waste from producing an entirely new fan and just allowing them to buy the individual parts. In conclusion, the benefits that we came across was we were able to greatly ease the assembly of our fan due to our large reduction in our fasteners. The drawbacks was we had a minimal efficiency increase with our redesign. Reflecting on the desk fan, it was a tough redesign based on the wide variety on the market and the small number of parts associated with it. And the variant that we chose also had a limited amount of metal components, which posed problems for our redesign using sheet metal and machining processes.